This day I can only start, and I'm surprised that nobody else did it, with a celebration, something that, celebrates the day. May the 4th be with you. Nobody smiles? Okay. This is a non-technical session, so I prefer myself not to be here, but to be in another room to attend more technical sessions. But this session here, with a Latin title, Calculemus, which is Latin for let's calculate, is the reason why we have a job today in this industry, is the reason why a conference like this, called Camp, and all the other conferences, the whole IT sector is running and thriving. Today, we inevitably hear a lot about the revolution of AI, but the latest revolution of AI, because AI started being a hyped term for years, but recently with the advent of transformers, ChatGPT being the most popular, the widest audience feels like AI is dooming on us, ready to take away all our jobs and changing the world. Interestingly, however, AI, but even more than AI, software. Software is something that started growing, okay, in the imagination of the mankind way back. And this session is about the journey that the mankind went through since the Middle Age. But I want to start focusing on one word, breakthrough. Now, quoting from a dictionary, a breakthrough is a sudden advance, abrupt advance, typically in knowledge or in some technological environment. Put another way, a breakthrough is an act of moving through or beyond an obstacle, is in a way something that enables you to do things that weren't possible before. And just thinking of software, I would say that the first huge breakthrough we experienced, I'm not sure because I cannot see exactly your faces because of the lights just in front of me, but I expect that all of the people in this room here is probably younger than me. So personally, the first breakthrough I experienced around software was with personal computing in the early 90s. After that, there was internet, e-commerce, and mobility across the millennium. And then, more than AI, I would say conversational AI. So the AI made possible, demonstrated publicly by transformers and ChatGPT, again, being the most popular. So a breakthrough is something that in the history of the mankind is what makes possible things that weren't just possible before. So we know AI, but we can even forget about AI as we got to know it for the past couple of years, because the public advent of ChatGPT open up the flutes for something that I like to call conversational AI. So talking to machines, humans that talk to machine. And with ChatGPT and all the OpenAI infrastructure that Microsoft has built on top of that, and with a lot of new software services being announced in less than 2 weeks at Build, end of May, it would be definitely becoming possible to talk to machines. How many books, fiction, movies showed us in the past decades the human, the character talking to a machine and the machine understanding perfectly the language and replying appropriately. The old mankind dream of talking to machines is now, apparently only now, becoming reality, but what very few people know, to my experience, is that this is a very old dream. Oops. November 22 is when ChatGPT became public. GPT stands for Generative Pre-trained Transformer, and in a sentence is a large language model inside of which something called a transformer, which operates bidirectionally, essentially maximizes the probability that a word has to appear next in a language, in a sentence, given the context the transformer has built. That's the mechanics. It's purely statistical. Well done, beautifully working, but purely statistical. This is what everybody knows today, but this is something that much less people know. There was a machine, I used the graphics that scratched it because that machine was never built. It was only the design of it. The conceptual design of it was prepared in the 17th century by Gottfried Leibniz. The machine was called a ratiocinator. And if you check out on Google, or if you ask ChatGPT maybe, it could tell you that around this machine, this conceptual machine called the ratiocinator, it's where the Latin sentence Calculemus came out. The ratiocinator is the concept of universal language that had to be, in the dreams of Leibniz, hardwired to a mechanical, never-built artifact. So if we compare these two, we have statistics versus the dream of turning the human way of reasoning into something that could be mechanically reproduced. Back to history. How could we go from Big Bang, well, probably not exactly the Big Bang, something closer to us than the Big Bang, to ChatGPT? We moved across this horizontal line thanks to the effort of a bunch of people. People who lived since the Middle Age to more recent years. Over this amount of time, it all started with the idea of one of these polymaths to research for a universal kind of language, different from the Arab, from the Spanish, from the Italian, the French, the English language, natural languages. Quest for a universal language, which became, century after century, the quest for a more solid foundation of mathematics and logic. When this step occurred in the history of the mankind, we are around the 17th, 18th century, the logic, what we call logic, which today is known to be a branch of the mathematics, at the time was still a part of philosophy. And it was driven by the ideas and the statements of Aristotle. So we made a jump, and some people rebuilt the foundation of logic and mathematics. In doing so, the whole theme of calculability, are we able to determine if a statement is verifiable according to logical rules, became an issue. Solved the point of calculability, we had everything to start building hardware machines, in which, at the beginning, think of the Second World War and the code breakers, the behavior of the machine was built not in a programming language, but through valves, through wires, physical combination of engineering pieces. And the final step, software, and hopefully intertwined with software, artificial intelligence. And here is the list, selected list of people who made this journey from, well, let's say, Big Bang to ChatGPT ever possible. So we will be spending the next minutes just analyzing the contribution that each of these 6 people gave to the journey from the quest for a universal language up to artificial intelligence as we know it today, and even more importantly than that, just software. Let's start with the first one. It's called Raymond Lull. That's the English name at least. He was a rich man living in the court of the Kingdom of Mallorca in the popular Balearic island of Spain. He had an interesting life. He was a rich man, very well introduced to the kingdom, and he was spending the first probably half, more than half of his life, up to his 40s, just entertaining people in the court of the king, playing musical instruments, writing and reading poetries. And at some point in his life, he decided that he had to drop everything to embrace the Catholic religion. It's not obvious if he ever became a missionary, but for sure, I mean, all historical sources seem to agree on this point, he acted as a missionary. And he also, in doing so, studied in depth philosophy, mathematics, and logic. Now, the reason why this person, and if you check out his history, his biography, he is often presented as a philosopher. The reason why his name is related, can be related to software, ultimately to software, is that he had an objective in his mind, okay? I am now embracing the Catholic religion. I want to be a Christian apologist. His goal was bringing the word of the Catholic God to everyone in the world. In particular, he focused on the North Africa. The time in which he lived, we are around the 13th century, was also the time of crusades occurring towards the other part of the Mediterranean. And he said, why should we kill each other to convince that one religion is better than another? Let's just use reasoning. So his purpose was finding a sort of a universal language through which the entire set of, let me say, limited, Catholic, restricted knowledge could be described so that he could go talking to Muslims in the North Africa and convince them with pure reasoning that the Christian God was highly preferable to the Muslim God. That was his purpose. To achieve that, he devised a sort of philosophical system known as the Ars Magna that we can describe today as a sort of decisional tree, in which there were a finite number of attributes per entity. An entity you can imagine to be like the root of a decision tree, and depending on the root you enter into the tree, and depending on the arguments raised in the conversation, the final destination of the reasoning was one of the leaves, and the leaves were restricted to demonstrate the superiority of the Catholic religion towards everything else. So he wanted to prove the truth of the Christian doctrine to everybody else. But in doing so, finite number of attributes, combination thereof, he ended up sowing the seeds of combinatorial analysis. He didn't achieve much. The legend says that he was killed during one of his attempts to bring this human reasoning in North Africa, but he left marks in history about combinatorial analysis. For 3 centuries, nothing happened. Then Gottfried Leibniz, and we are 3 centuries later, Leibniz, who made his mark, important mark in modern mathematics, calculus. We owe it, for the most part, to Leibniz, at least for the notation. But Leibniz got his degree in law. He studied law. And his dissertation was about reviewing a number of trials in the court of Leipzig, where he lived, and making a sort of post-mortem analysis of the reasons, of the reasoning that the judges went through to decide to give an outcome to those trials. So logic that in a way triggers a sort of a mental calculation to come to an outcome. So it took this vision further. It discovered the previous work from Lull and started envisioning a formal language much more perfect compared to what Lull did 3 centuries before, to reduce reasoning to calculation. And in yellow, that's the popular quote from Leibniz in one of his writings. If we could have this language, any dispute can be resolved by expressing the question in a precise language and use rules of calculation to carry out precise reasoning. So instead of arguing, instead of quarreling, instead of disputing, 2 gentlemen can just say, hey, Calculemus, hey, let's calculate and see who is right and who is wrong. This was the dream of Leibniz. Now, Leibniz, in the machine called the ratiocinator, just devised, conceptually, how it could have been done. More concretely, however, Leibniz physically built a calculator, this time a calculator, called the step reconer in English, which for the time was the most advanced piece of technology. Before Leibniz, who created the machine able to perform all the four arithmetic operations. Before that, there was a machine called Pascalina from Blaise Pascal, who was only able to perform 2 operations. Apparently, the first commercial electronic calculators from Texas Instruments put on the market in the 50s of the past century, 1950, were essentially identical internally to the stepped reconer project from Leibniz. I have no idea if this is true or false, but you find references if you Google around for this kind of statement. Unfortunately, Leibniz, for his entire lifetime, had one huge problem: money. So apparently, he never carried out the project of the ratiocinator because he never found someone that could pay him for just doing his own things. And so we had to wait more centuries until this ratiocinator machine could come to life. Anybody here ever heard Gottlob Frege? He's a German logician. This is one of the unluckiest men in the world. He wrote a piece of paper, a book, that is the first piece from which the entire logic of first order that everyone studying computer science knows, logic of first order, was coming out from the work, the book that this guy, this man, had to pay to publish. He couldn't find not even a publisher willing to spend his own money to publish his book because he was considered completely crazy. Leibniz only sensed, okay, that a tight relationship could exist between algebra and logic. So the logic that could be taken away from the realm of philosophy to land into the realm of what was at the time the vision of mathematics. But Frege was exactly the person who made this, who demonstrated that this step was possible and due. He was an extremely unlucky person because when he was ready to, towards the end of his life, to print a second book with the entire theory, he received a letter from another relevant individual, Bertrand Russell, saying, "Oh, sir, dear sir, I deeply appreciate your work. I couldn't find anywhere else a treatment of logic deeper as yours, but I only have one problem with your statements. I have a counterexample." So the counterexample, today called as the paradox or antinomy of Russell, was not just a counterexample for the work of Frege. Frege didn't put any bug in his own work. It was just a much deeper question that the same Russell, and I have to mention, to reference what Kevin mentioned during the keynote after lunch. He mentioned the Principia Mathematica by Russell and Whitehead, published in 1911. In that paper, they overcome the counterexample he found for the work of Frege by essentially introducing a precondition that made it impossible for the counterexample to show up. He didn't solve the issue, okay? He just found a workaround. However, the work of Frege and the contribution of Russell raised, and we are across the beginning of the 20th century, led David Hilbert, another relevant German mathematician, to list the problem in yellow. Can all mathematical statements be expressed and manipulated through a set of well-defined rules? Is this possible? Question mark. This question mark was put in the list of open problems that Hilbert identified in 1900, hoping for someone in the new century to solve. So the ultimate purpose of Hilbert was to find, to figure out whether or not it was possible to find a set of axioms to derive all mathematical statements. Look at the year in which this new scientist, Kurt Gödel, died, 1978. I was a teenager at the time, so we are really close to our days. Kurt Gödel, in the 30s, formulated the incompleteness theorem, and I have to again re-reference something that Kevlin mentioned during his keynote today. In yellow, in any formal system expressive enough to model the arithmetic of natural numbers, there is at least one undecidable statement that evidence proves true, but that cannot be proven true or false using only the rules of the system. So basically, with this theorem, Gödel proved Hilbert wrong. So no, the answer to the Hilbert question is no, it's not possible to express the whole world of mathematics through a single set of axioms. Because we will always find a statement that seems to be true, evidence proves true, but cannot be proven true or false through the rules. But at the same time, if we restrict this, the boundaries of our system, then it's definitely possible to determine the calculability of every statement that can be expressed to the set transformation rules that the logic of the system places. Again, back to Frege, the logic of first order, put in a context in which no counterexample can show up by design, is what we call programming languages today. So with this theorem, we have the mathematical demonstration that a programming language is possible. Then Alan Turing. Turing and Gödel were living at the same time. They were friends. They knew each other at least. And at the same time, around the mid of the 30s, Turing, Gödel, and another American logician, Alonzo Charch, each of them created one of these systems that could express the calculability of any expression within the system, the lambda calculus, the recursive functions, and the Turing machine. And Turing also demonstrated that all these three systems were interoperable. So if an expression is calculable in any of the three, is then equivalently calculable in any other. So they were the same thing, logically. And then Turing used his own calculation model, the Turing machine, equivalent to lambda of Alonzo Charch and to the recursive functions of Gödel, to create the machines that during the Second World War helped to crack the Enigma Nazi code and probably saved the lives of many, many, many people. Okay, beyond Second World War, John von Neumann. Anybody who studied computer science knows John von Neumann. The von Neumann architecture is still the, no matter harm, risks, and progress, but the core of the modern computers is still the von Neumann architecture. And von Neumann, friend of Gödel and Turing, he is the man who separated within a machine what is hardware from what is software. So hardware and software are two terms that we owe to John von Neumann. He started envisioning that, okay, if we want to build a machine that can at some point mimic the human reasoning, we must be able to provide the hardware instructions and that are not hard-coded with cables and valves and transistors and whatever else, but with text, with instructions. So hardware and software. But more, John von Neumann unfortunately died too early when he was 57 or 54. But he also studied deeply the structure, as a biologist, the structure of the human brains, synapses, and the neuronal architecture of the human brains. And he also started planning a computer architecture that had, in the 50s, okay, a neuronal architecture. He died too early, and for all the next decades, nobody else ever thought or was ever able to resume from where he left. Today, we may hear in academic environments, I think the last one was in Australia around last year, of research teams that come up with neuronal architecture for computers, but it's nothing that now is close enough to become commercially available. Okay, John von Neumann. Now, after that, we had software. We had software, and software is a waste product. So the human dream was to mechanize the reasoning, the human reasoning, and John von Neumann created the entity called software. So for a few years after, in the 60s and the 70s, the purpose of the research was, okay, now let's build software that could reason as a human. Machine learning started, the first algorithms, the first concept of a neural network dated those years. But they quickly figured out that it was extremely problematic to repeat outside what we call today an expert system, which is a finite decisional tree, okay, something that could resemble the human brain's activity. But at the same time, they found out that, however, for a number of business scenarios, including going to the moon, performing the calculation of the orbits to go to the moon, software was extremely useful. So we had software, and the term software engineering appeared for the first time at the NASA conference in 1968. In the mid-70s, we had Dijkstra, and making word about the universal principles, cohesion, coupling, separation of concerns. So software took its own route, started a different journey parallel to AI. AI apparently dead for a number of years. We developed software, but software is essentially a waste product of the research for ways to automate the human reasoning. Universal language to mechanize reasoning, and today ChatGPT brings us to software that apparently understands the human language. But along the way, we had to go through the redefinition of the logic foundation, building physical machines for fixed hardwired tasks, software and hardware separation, and then question, how to write software that emulates reasoning? Just go with business software. It's much easier for everybody. And after going enough with regular software, neural networks started again to evolve. I graduated in computer science in 1990, and people who graduated at the same time as me were discussing, defending theses about neural networks, the state of the art of neural networks in the late 80s. Nothing has happened for 20 years. And then with the millennium, news that became public only a couple of years ago, Microsoft started working on neural networks internally to create features within PowerPoint, Word, and Excel. They were baked. Nobody told us, but now we know that they were, those functions were baked by exercises of machine learning. So neural network evolved, and then 2010 and its recent history, they rocketed and became ChatGPT, a software that seems to understand the human language. So from this machine, processor, a formal language to express thoughts and arguments, to mere calculation, to ChatGPT, which is a neural network that works to build and understand the context to figure out only the next, the most likely word in a conversation. Now, at the time of Leibniz, Lull, and all those polymaths of the past, the processor of a formal language to express thoughts and arguments and reduce disputes to mere calculations had no need to be sentient. Because humans, in the vision of those times, were just instruments in the hands of God. Leibniz said exactly that. Today, instead, we have that ChatGPT, or GPTs, are not yet sentient, and humans, instead, let probably the AI to instrument them as the AI were God. Today, custom solutions, commoditized across services that Amazon, AWS, Microsoft, Azure expose, cognitive services, speech-to-text, text-to-speech, OCR, all those things, NLP, commoditized services. In the industry, we also have a custom solution. So we have a problem, a company has a problem, prediction of energy being produced by wind turbines. It's a problem that requires a lot of intelligence, learning from the past. Okay, so it's a custom solution. It's not something that can be commoditized and used to build other solutions. Today, and even more tomorrow, in the coming weeks, with the expansion of the OpenAI platform on Azure, we have commodities specifically in the area of cognition, and this opens up conversational programming, in which there are three pillars: data and model separation. We are not talking about software. The model is the machine, the pre-trained, generative transformer machine. The data is your data. This is the scenario of the near future. You take your data, whether it's a database, whether it's we made just last week in the office an exercise, astonishingly amazing. We took the URL to the Swagger URL of a public API we had. We passed that as our data to the OpenAI GPT service, and we could chat with the API. Which method I have to call to achieve this? And the only data, our data, was the commands in the code. It was possible to chat with the API with no need for a standard canonical documentation. So that is one possibility. To achieve that, data and model separation and produce working software, we need to resort to a new flavor of programming language. It's called, at the moment, prompt engineering. It's essentially understanding, engineering the prompts, the messages, the instructions to be provided to the GPT in order to establish a conversation. This said, we have new security challenges. AI, in the end, is just software. So AI is just software. Thank you very much for your time.